Factors influencing rate of a reaction. In that one, chemical nature of reactants. How this chemical nature of reactant influencing the rate of reaction. 1. For example, reactant convert into product. One example is now 2NO plus O2 that is converted into 2NO2. This is in gaseous state. Now here N double bond O and here one lone pair because nitrogen having how many bonds? Three bonds and one lone pair. Now here one bond, this one dot also, here lone pair and lone pair. This is oxygen double bond O. This is converted into N, 2N double bond O. Totally here, how many bonds are there? This is 2 times. So, in this molecule, I am counting these bonds. That is, these bonds, 2 bonds. Here also, 2 bonds. And here we have 3 bonds. 3 bond into 2, that is called 6. Here 2, here 2 into 2, that is called 4. So here 2 molecules are there, therefore 2 into 2, 4. Now overall how many are there here? 4 plus 2. That convert into which one? 6 bonds. Now we will take the another example. Methane CH4 plus oxygen, that is 2 moles of oxygen, convert into carbon dioxide plus 2H2O. Now here methane, it has the 4 bonds, and this is 2 double bond O, and this will be converted into double bond O carbon. This is plus 2 moles of HOH. Now you consider here 4 bond, 2 into 2, that is a 4, and product side is 4 bonds plus this is 2 into this 2 bond, this also 4 bonds. So overall product side 8 bonds are there, and here also 8 bonds are present. But in the first reaction 6 is there. So based on this, in reactants, rate of reaction, that is inversely proportional to the, it means less number of bond means faster, more number of bond means slower. So number of bonds in a reactant, this is the rate of reaction depend on number of bond. Sometimes rate of reaction depends on product also. Now rate of reaction is directly proportional or inversely proportional to the product number of bonds. We'll check now. Example here, I will take here what you call this CH3OH. This is convert into CH3O minus plus H plus. Now I am taking one more, that is called CH3 C double bond O, OH. This will be break and convert into CH3, C double bond O, O minus plus H plus. Here number of bonds or breakdown is both. Here also one bond break, here also one bond break. Both are having same number of bond breakdown, but we have to decide which is a fast reaction, which is a slow reaction. So this is called slow reaction. This is called fast reaction. How to decide this fast or slow? Because we know that this is little relatively compared with this alcohol, acids are stronger, this is weaker. Now actually acetic acid is a weaker acid, but compared with the alcohol stronger acid, then easy to lose H plus, tendency to ionize increases compared with the alcohol. Therefore now it decides that this is a stable anion, this is a less stable anion. When it is less stable, difficult to form to the product, then it is more stable, it is readily form the product. Therefore rate of reaction is directly proportional to which one? Stability of product. Stability of product. Next, in this one, nature of reactant, physical state also important. Physical state. Now, in physical state, we have the gas physical state, liquid physical state, and solid physical state. Reaction carried out in the gas, that is a somewhat faster than the liquid, liquid are faster than the solid. Again, in gas, we have two types. One is homogeneous, another one is heterogeneous. Homogeneous reactions are faster than the heterogeneous, similarly in liquid also. Next, in the solid, we have large surface area and small surface area. Finely divided form. Finely divided form. Another is a normal solid form. Larger particle. Finely divided form has a large surface area. This is a smaller surface area. Therefore, larger surface area has a larger rate, so rate of reaction increases than the larger particle. Finely divided particle has a larger surface area, therefore they are fast reactions, and this is called slow reactions. Next, second one is a concentration effect. In this concentration effect, this is somewhat common. Explanation of concentration effect is a complex, not that much easy to understand, but according to our textbook given, this rate is directly proportional to the concentration power n. It indicating here rate of reaction is directly proportional to collision frequency. Collision frequency is directly proportional to the concentration. So this is very important. Rate of reaction directly proportional. Collision frequency directly proportional to the concentration. So more number of reactant molecule, higher the rate. Less number of reactant molecule, lower the rate. Next one. This detail we'll discuss in the rate law. This is about the concentration effect. Now, third one is temperature effect. Temperature effect. Here also again same rate of reaction that is directly proportional to collision frequency. Then this collision frequency directly proportional to which one? Energy. So if you apply the some amount of temperature, then automatically rate of reaction increase. This also separate discussion is there next. So temperature increases, rate of reaction also increases. Every 10-degree rise of temperature, rate of reaction nearly double. Every 10-degree rise of temperature, rate of reaction nearly doubled. That is called rate constant, nearly doubled. Next one is fourth. In the fourth, what is there here? Catalyst. Catalyst increase the rate of reaction. Catalyst is increases the rate of reaction by giving alternate path, by decreasing activation energy. Anyway, catalyst increase the rate of reaction. Catalyst is substance which increase the rate of reaction without undergoing any chemical change in the reaction. So it decreases the activation energy and convert into the product, because we know that rate of reaction is directly proportional to which one? Collision frequency. So number of collision takes place, meaning the path activation energy should be lower required. Next one is fifth, intensity of light. Rate of reaction is directly proportional to the intensity of light. This is one explanation. Next one, already I told you that sometime pH for acid-base reaction, sometimes lower required, sometimes higher required according to condition. That's why, because some cases H plus and high required, some cases H plus and lower required. Therefore, pH increase or decrease, both cases rate of reaction increases according to condition. This is for acid base reaction. Now, one example I will give for this pH. We know that corrosion of iron, that is called rusting. Rusting is catalyzed by H plus ion. So we already learned that at lower pH, rusting of iron rate is increased. This is one explanation about the how the rate of reaction is influenced by the some factors. Now we'll deal about the rate of reaction, how it depend on the concentration, that is called dependence of rate on concentration. Detailed discussion. Dependence of rate on concentration. How it depend? Already I given rate is directly proportional to concentration power n. So now I am taking one example. A moles of A, B moles of B gives rise to C moles of C, D moles of D. Now, in this reaction, rate of reaction expressed rate is directly proportional to the concentration power X, that is concentration of A, and concentration of B power Y. Now, here X and Y are may not be equal, or may or may not be same as coefficients. What are the coefficients like A and B? They are not same. Now, this can be explained as rate is equal to, or rate proportional to removed mean place the constant k, A power x, B power y. Rate already we know that minus dr concentration by dt, rate of reaction, that equal to k, A concentration power x, B concentration power y. This is only called rate law or rate equation or rate expression. So now we know that this is called rate and this is called rate constant, square bracket is called concentration. A and B are reactants and X, Y are may or may not be same as stoichiometric coefficients. Then how we know this X and Y? X and Y are known experimentally. Therefore, rate law is experimentally determined. Now, what is the rate law? According to this, rate law definition. Rate law definition. Rate law is the expression in which reaction rate is given in terms of molar concentration of reactants with each term raised to some power, which may or may not be same as stoichiometric coefficient of the reacting species in a balanced chemical equation. One example I given here. So according to that, rate is equal to K NO concentration whole power 2 O2 concentration. Now, in this one, this rate is expressed in terms of molar concentration of NO and molar concentration of O2. Square bracket means concentration. Each term in here NO and O2 raised some power in here 2. Here how much? Nothing is given mean that is a 1. These powers may not be same as stoichiometric coefficient. Now here stoichiometric coefficient of this reaction is 2 and here nothing is given in 1. So these are equal here. Therefore now x is equal to 2, y is equal to 1 and these are equal to stoichiometric coefficient. Now, if I write any other reaction that may not be same as the stoichiometric coefficients. For example, here given is chloroform plus chlorine convert into CCl4 and plus HCl. If I write rate law for this, rate is equal to K CHCl3 concentration power 1 and Cl2 concentration power 1 by 2. Then overall order, that is x is equal to 1, y is equal to 1 by 2. These are may not be same as a stoichiometric coefficient. Yes, stoichiometric coefficient 1 is there and here 1 is there, but this is not equal to this 1 by 2. That's why keep in mind this is experimentally determined. One more example here, that is CH3COO C2H5 plus H2O gives rise CH3COOH plus C2H5OH. Its rate law is given as rate equal to K CH3COOH, sorry, CH3COO C2H5 concentration and H2O concentration. This power is given here 1 and here 0. So here stoichiometric coefficient of this reaction is 1 and this reaction 1. But here stoichiometric coefficient 1 is matching, another is not matching. Therefore x is equal to 1 and y equal to 0. Here stoichiometric coefficients are not matching with the powers, each term raised their powers. Therefore, rate law is experimentally determined and these powers of the each term, each concentration term is known as order with respect to that reactant. Therefore, order of reaction experimentally determined but not deduced from a balanced equation.